We are going to keep on moving, and our next speaker is Dr. Andrew Margenot. He is a soil scientist and associate professor at the University of Illinois, Urbana-Champaign. He's been here since 2017. That's it? It feels like you've been here forever. Okay. He has worked to address soil and nutrient management challenges facing Illinois agriculture. He leads a research team that evaluates the biogeochemical mechanisms that underpin soil functions with a focus on nutrient use efficiency, organic matter cycling, and mitigation of nitrogen and phosphorus losses to surface waters. Dr. Margenot.
Thank you, Julie. Okay, I was asked to speak today about the phosphorus part of our program that is funded by NREC dollars, and that's my goal today. So as Julie has said, I've been here since 2017, and our team really has been hard at work with support from NREC, trying to tackle this question of having our cake and eating it too. So these trade-offs we often see or hear about between the goals of crop production with environmental quality. And the focus of today is to walk you through some examples of where I don't think that there's a zero-sum game. There's obvious opportunities to maximize and maintain high crop production and to minimize losses of phosphorus to water quality. So that's the goal of today, and I'll take you from scales that go from hours to centuries, and spatial scales that go from a peton or an aggregate all the way to the state scale. And the goal is to showcase some of the progress that we've been making with NREC funding towards meeting these dual expectations being put on phosphorus and really on agriculture in our state. First, I want to acknowledge the folks that have made this possible. It's a small army of students and technicians and collaborators, including farmers across Illinois, that have been very generous in letting us go on their fields and sample soils for the legacy project that you will hear about more soon. Okay, so first, a bit of background. I want to set the stage and at least share with you how I approach phosphorus and the overarching philosophy that our lab has. There's a need, I think, to reconcile that what matters for agronomy and crop production is not the same magnitude-wise as what matters for the quality of water. And this is a tale of two different magnitudes, the how much. So if we think about the MRB, we can think about hotspots of losses. Across the 31 states in the union that drain into the Gulf, we have an average of 1.6 pounds of P2O5 per acre being lost. So that's an average, and it's everything from parts of Montana with no ag going on to the Corn Belt. So if we focus in, on the Corn Belt, which is the upper basin subsection circled here, this is the most productive swath in the Union and the MRB and arguably in the world when it comes to grain yields. It's also the highest subregion of P losses of the Gulf, or of the basin. And so we're losing about 2.7 pounds of P2O5. Not a whole lot agronomically, right? We're putting on, with 200 pounds of DAP per acre, 96 pounds of P2O5 per acre. So pretty small, but the hot spots here, we're not talking 50 or 80 pounds of P per acre. We're talking less than 3 pounds of P2O5, which on a P basis, not P2O5, would be something like 1 or less. At the same time, when we think about the relative P use efficiency of our inputs across the same basin, the basin, and more specifically, the Corn Belt part that is responsible for driving high yields, the I states, are some of the highest, if not the highest, P use efficiency counties in the country. And that's especially given the global average of 16%, albeit with a different technique, but the point stands that within the basin states, the highest yielding, highest use efficiency are also the highest losers of P. And that seems like an apparent paradox, of course. And I've said this before, that there's no paradoxes. We're missing something big time. We need to figure out what's going on. So this P paradox, I think, can be collapsed or reconciled if we consider, again, these magnitudes are just different. So how could it be that we are the highest P use efficiency states in the Corn Belt and the basin, but also we're losing the most? And it comes down to what I just mentioned, that we're adding a lot of phosphorus for crop yields. We need to add this P to replace what's taken off with harvest. That, to me, is sustainability, is a maintenance rate. And yet the hotspots don't require very much phosphorus. And if we think about the math here, To be a hotspot in the basin, we have to be losing only 3% of our P application. And that is assuming that all that we're losing is from fertilizer, and as I'll argue shortly, it's not. That's the minority when it comes to contemporary applications. So to put this differently, even if we're at 97 PU sufficiency, as a percent, which is quite high, again, global is 16, most counties in this country are 80% max, that still leaves room for very large negative impacts on water quality. Let's take this further. Let's push the argument further. And that would be that we cannot use efficiency our way to reducing P losses. And this is in contrast to nitrogen. So we might see in a very wet year 40, 50 pounds of nitrate N coming out of tiles in some very bad years, and an average of easily 20 to 25. And if you're putting on 180 pounds of N per acre, now 40 pounds is quite a large percent. So for nitrogen, we can realize reductions in nitrate leaching and gas losses as well by pushing N-use efficiency. But for phosphorus, that's just not going to happen unless you're maybe hitting 99.5% P-use efficiency, which is unspeakable. That's not really going to happen. So I'm not dismissing this, and also important to caveat, where we are right now, which is a very high P-use efficiency status, any further gains and P-loss reductions won't be coming from P-use efficiency increases, because we've done a good job of being efficient with it already. So this means that also, the bright side, we don't have to compromise yields when it comes to thinking about phosphorus and loss and how we achieve these reductions. Unlike N, so for example, if we cut back the N rate to 100 pounds per acre, yeah, we'll reduce nitrate leaching and we'll have terrible yield drags. That makes no sense. Unlike N, for P, we have more wiggle room here because of the decoupling of the P-use efficiency and thus yields from the P losses. So that's the bright side. So can we have our P cake and eat it too? That sets the stage. And I think, yes, we can have the cake. And the way that we're trying to tackle this with our NREC projects is as follows. We want to understand and move forward in lockstep the basic understanding and then the applied aspects. And applied is not just how to do a practice on a farm, that's part of it. It's also how we pre-chew the results and digest it for policymakers and the public who have a role in all of this. How we do this is for spatial scales, we go from PET-on profile all the way to watershed, and if that sounds exaggerated, I will show you how we do that. And temporally, we're going from hours and seasons to the course of over 120 plus years. And that's how we get the cake, I think. So 3 major aspects or thrusts of our program that I'll share with you shortly. One is updating, but also expanding and even reimagining how we conceptualize the use of phosphorus to support high crop yields. There's some good stuff that's been done that we can build on, but I think we should also be a bit creative. Second is how we improve source apportionment, which is where is the phosphorus coming from? And as we'll talk about, we've made some really good gains in this state by being able to begin to decompose the non-point source sector into sub-non-point source sectors. So agriculture, streambank erosion being 2 primary non-point sources. And building on that is legacy phosphorus, which frankly integrates the first 2. And we'll talk from field to stream, soil to stream. There's 2 kinds of legacy phosphorus that present what some call a wicked problem. That is what people call this in the field of phosphorus work. It's a wicked problem because it's very hard to get your hands around it and to solve it. So we'll talk about legacy P in soils and legacy P in the stream channel. It's already in circulation and what that means for our reduction targets. So with that, let's buckle up. We're going to begin at the small scale, small spatial scale, and then we're going to get down and end on the state scale. So the smallest scale is the top 3.5 inches of soil is what we're going to look at first. And I want to here talk about some of our work with NREC on struvite is basically slow release MAP fertilizer. You got magnesium tacked on there and the dissolution rates decrease. And as a proof of concept, here's an example of what the basic science can do for the applied science. So the basic science part here was to compare if you've got struvite and MAP and you're trying to understand the fate of it, P use efficiency for crop uptake, not shown here, but also just P losses. There's two ways to trace where's my fertilizer P going. One is the common indirect approach, where it's by difference. You have a unfertilized P check, you've got your fertilized P, and by difference, you can attribute the P that was leached or was just lost versus what was used by the crop. So that's indirect. You're not actually tracing the flow of phosphorus. The first one is the direct approach, and this is hardly done for phosphorus. We don't have more than one stable isotope, unlike for nitrogen, so we can't label the P and follow it. We have to use radioactive phosphorus. It's unstable. As it decays, it gives off radiation. So using this novel approach has been not really wielded that much for obvious reasons of its radioactive phosphorus. We are able to synthesize MAP and struvite in the lab and follow the literal atoms of phosphorus fluxing through the system. So one of the findings of this is that for the first time, we're able to show things like early season corn uptake from MAP and struvite, but the point to emphasize here is that we confirmed what we see in the field. We get the same yields using struvite instead of MAP, which means that point sources that make struvite to hit their P maximums can now recycle the struvite as a source of phosphorus. And we see that these decreases observed in the field are corroborated in the lab with this technique. That's the basic science. Here's the more applied, or the implications rather. We find that when we use the indirect approach, which is what everybody does in agronomy, we're overestimating the P leached from the MAP or the struvite by up to 54%. We're not sure why this is, but it means that we're counting atoms of P that are from soil and not from the fertilizer. So we're overestimating the losses of the fertilizer that same season. In that same study, we wanted to understand how much of the fertilizer was being lost. 0.2% of the application over 2 years' worth of rainfall simulation. So we pushed 112 inches of rainfall through the top 3.5 inches of soil in the lab setting, and we only got 0.2% leached out. Now, runoff losses are a major pathway, but this suggests pretty minimal fertilizer same season losses. Okay, now what we found was that most of the P was lost in the first year of rainfall equivalency, and we see that on the graph on the left-hand side. By 21 pore volumes, that's a year's worth of precip. So to explain this, and as an example of leveraging NREC funds, we're able to try to do some basically MRI, three-dimensional analysis of soils from which we can develop a pore network. And this pore connectivity is a big determinant of how P moves as dissolved form through soils. So the goal then is to understand why there's this initial one-year flush and what could be explained in how different soils managed in different ways, why they lose different amounts of P by leaching. So this is a good example, I think, of the work that we're doing that is leveraging NREC funds to understand the mechanisms more. Now let's get a little bit larger scale. We're gonna telescope up to the field scale. And this has to do now with the state agronomy handbook and the RECs. The overall value, I think, of this handbook, among a few other things, is this number right here. What's the critical value on your soil test that you want to be above to avoid a yield drag? And if you're beneath that critical value, it would justify an application. A lot of issues with these numbers. They're outdated, they're not crop specific, the sampling depth could be checked out. We're trying to address these and other issues through classic on-farm trials. So think of this like the MRTN trial approach. Well, same thing for phosphorus. And so as an example of the first year results, this is year 1 of year 4. So that's the caveat. This is not a whole lot of field sites. We see that already there is some value. So for example, we find that there is a critical value of roughly 34 pounds of P per acre. Again, a small set of sites, but that's a little bit lower than the current handbook. Now the scatter on that plot is pretty high. And I think that we should not dismiss those as outliers. That's where the message is. So here's an example. That field right there is not responding to P, even though it's at 10 ppm. So that would suggest that for that field, the critical value is beneath 10 ppm. You don't need to get up to 20 or 25 ppm. And the field down there is still missing out on potential yield by not adding P, meaning that its critical value is in reality much higher. It's around 40 plus ppm. So whenever we have an average, like one critical value for a state, by definition, half the fields will be above or below as a concept average. And here's an example of what we've been able to do on maintenance rates from some NREC work in Bureau County. So if we think about the handbook values that inform maintenance, for every bushel that comes off the field, how much P2O5 to put back on, these are based on these handbook values, and they're based on the 75th percentile by and large. So the 0.37 pounds of P2O5 per bushel of corn that comes off, that you then use to estimate what should be put back on, well, that's using a safe value of the 3/4 highest level. But that again means that by definition, given this distribution, some fields will have over or under application. So this is the problem with averages. They're really useful and they're a good first step, but I think the next step is to rethink, can we make these more field specific? So here's an example from work in Bureau County, and what was done here was sampling 12 fields over 2 years, corn, soybean, and the values that you see here are shown next to the horizontal lines of what the handbook concentration of P is for the different percentiles. And what you can make out is that for corn, and then also for soybean, by and large, most site years were not even near the 50th, let alone the 75th percentile of the P2O5 content. So if a farmer is applying based upon the assumed handbook value for these fields, they're over applying beyond what they actually need to because the P content is lower in the grain at these sites. So this is not a knock on the handbook. We need an average. But then the question is, could we rethink how we do maintenance applications? So why not measure the grain directly? We spend a lot of money and time on soil testing. Why not measure grain values to inform VRT P applications? The yield map is one of the two steps. The second step is pull a grain value on a grid, like we pull soils on a grid, and can we refine how we apply based on the maintenance? So speaking of VRT, that brings up the question of economics. And this is the question of, is the P paying for itself? And so I'm sure that Dr. Jones has lots of thoughts on this, and there's a lot of healthy debate, I think, going on from Iowa State on why don't we rethink dollar per acre return versus the yield, the bushel per acre. This is not a new idea. There's a lot of evidence shown here from 1908 that this is how the first soil scientist, arguably at the U of I, Dr. Hopkins, was approaching it. And as you can see from his notes here, he's really talking about the return to phosphorus. That return, by the way, is super high at 272 dollars per acre. These are also low P soils in 1900. So for this, what we're trying to do with NREC funding, which we've leveraged for NSF funding, is what you heard from Dr. Guan this morning. We want to make a MRTP. There's one for nitrogen, why not two for phosphorus, and K for that matter? There's evidence that it might be easier in some respects for P to get more field specificity. There's things like soil test values that can be plugged into an online tool, unlike for MRTN. And there's things like Surgo maps that give us soil type maps. So this, I think, holds a lot of promise to refine economic use of phosphorus with the co-benefits of avoiding high buildup rates that aren't needed and our liability for runoff losses. So going back to the handbook, there's this concept of subsoil P supply power. I think lots of folks have heard me talk about this in the past, and those that don't know, the whole idea is that the critical value is predicated on this idea that what's beneath the top 7 inches is offering phosphorus to the crop. How much is that? So let's talk about the origins of this. This summer, we made a nice discovery in a closet on campus. We found some of the notebooks of Dr. Hopkins. So this one here is from 1901, September 1st or September 4th is this entry, and there's good data on the sampling location, and there's the data on things like phosphorus content, which we believe was being done pretty accurately. So these notebooks are valuable because it shows that they were in the effort to try to map nutrient stocks, not soil types, first and foremost. So to give you a better understanding of where this concept comes from, if you look at these notebooks, there's a lot of talk about by depth, how much phosphorus is there, and then as a result, the full profile, how much P is present. And these are some of the raw data that you're seeing from his notebook, 1901. And then in a separate writing, he publishes this idea about, of course, some of the phosphorus taken up by the crop will come from the subsoil. Note the of course, that really is striking to me. This was an obvious thing back then. I think that they lack the ability to quantify it very well. Measuring total pea stocks to depth is a good first step. Also note on top that they're tipping their hat to this concept of legacy phosphorus, that there's going to be P built up from past applications. Okay, so we can use this archive of soil samples that we have that were used in the original soil survey of the state. Oldest one is from 1861. And now with this new data set, it's not samples, but the notebooks have data on P content pre-1915. We can couple these and understand a lot about soil phosphorus, especially pre-input period when we were using just nothing. And we can also understand the changes in phosphorus in soils over time. And that's how we get at legacy phosphorus. So here's some examples of this. We can understand how accurate the handbook concept is of subsoil P supply power by looking at the map on the left that we've actually measured P4. These are P stocks to 3-foot depth across the state. And we show here roughly how they agree and don't agree with what's in the handbook as the regions. So the next step is to actually quantify the contributions, but the first step is this. We're really finishing the work that Hopkins began with those notebooks. He died in 1915 from malaria preemptively, so we don't really know what he would have done. I think he was only in his 30s or so. So we can also resample these locations. There's great data on the location, and right now we have 463 locations that we have high confidence of where the sample was taken, not just when it was taken. And the map here shows you all the sites. The ones in green the ones in red have been sampled, roughly 1/5 of them. We have another 13% lined up for sampling, which means that we will have sampled roughly 36% of these sampled by end of the year. I want to pause and thank those that have helped us on this. It's been quite useful, and we need the help of people like yourselves to get out the word. We want to finish sampling at least half of these 463 sites. And so that's ambitious, but we can learn a lot about phosphorus and soils in general. So here's the QR code if you have time to take an image. So currently we are underway with the analysis of all of these archived soils and then the resampled one. Here's an example now of why resampling is invaluable to understand why is Illinois losing phosphorus even though, as I'll show you soon, we're not over-fertilizing with phosphorus. So one would be legacy phosphorus in soils. Here's a snippet from just 5 of these sites that were resampled. There's 2 in Adams County, same time period elapsed from original to modern sampling, 2 in Gallatin County and 1 just north of us here. And what we can make out is that there's large but variable negative P balance or change in P stock. So we have lost 1,000 pounds of P per acre in one of the Adams sites, but just 100 in the other. And then we get smaller but largely, well, just all positive increases in P stock for the other 3 sites. This is all good. Now, why am I talking about this? Well, if we can, at the watershed scale, not the field, but the watershed in which we find these fields, if we can extrapolate and understand what's the change in phosphorus stock, a positive P balance that led to accumulation of phosphorus over time might help explain why in some Huc-8 watersheds we see, for some reasons, unexplained in some years, a sudden increase in P losses. This is how we get at the legacy phosphorus in soils. Without this, and we're lucky that we have this archive, we're just making estimates off of mathematical balances and certainly not sub-county or watershed level. Why does this all matter? Well, let's go back to the more recent 5-year average update that was published, where we saw that from 2017 through 2021, there was a 35% increase, which is 12 million pounds more phosphorus lost from the state, meaning export to the Mississippi, than the baseline. That's the wrong direction that we don't want to be going in. And at the same time, as we know from some work that Dr. Mark David and Lowell Gentry have done, that we have been in a negative P balance in cropland since 1990, and that our current NREC work is pointing out persists as a negative balance since 1990. So the negative balance means that the inputs as fertilizer, as manure, are less than what's coming off the field as grain harvest, or with the grain harvest. So some great work by Sean at SIU Carbondale as part of this collaboration with U of I and SIUC. We were able to look at the same exact time period. So I'll remind you, we're looking at the 2017 to 2022 period that we saw a 35% increase. And we see that in 2017, the beginning of that 5-year average, we had a negative P balance of roughly minus 7.4 pounds of P per acre, and that's P, not P2O5. And then 5 years later, still negative. Yet we see a 35% increase in state export of phosphorus, and we've been in a negative since 1990. So this is another apparent paradox, right? How can this be? Well, it would suggest that what we're losing from the state is not coming from contemporary fertilizer applications as an average. Yes, some locations, some counties are positive balance, but as a big state scale, spatial scale, this seems to be the case. Now, for manure, we did look at with and without manure in these balances, and long story short, the inclusion of manure phosphorus decreases the balances to be less negative by 3 pounds per acre. So in 2017, they're only -3, not -7, and they're just about 0 in 2022 instead of -3.9. So this is important because it means that manure, it's not a huge source of P in the state, but it's definitely having a big impact. Also, I'm not really comfortable with balances based on manure because of the assumptions that one has to make. P2O5 content of MAP and DAP by law is certified. Manure, you just got to make a call on it. The other bigger point here is that we're not over-fertilizing with phosphorus, and this is pretty remarkable that we're pretty close to neutral. We're not deeply in the red or largely positive. So this is one kind of, so that collapses this apparent paradox of how are we losing all this phosphorus if farmers aren't applying over what crops are taking off? Well, one hypothesis is legacy soil phosphorus, what the archive affords us quantification of. The other one would be legacy phosphorus, but in sediments, in sediment form, inside of channels already. And this is where streambank erosion comes in. This also brings up a greater discussion on apportionment, which is simply a budgeting. Where is the P coming from? And specifically within the non-point source sector, disentangling within that green part of the pie, the half of our P that we think is non-point source, what is ag, what is non-ag? And for the non-ag sources, are these legacy sources, are these streambank sources, et cetera? So I'll focus on streambank erosion because I think it is a poster child of an overlooked, orphaned non-point source, the missing of leading to a lot of uncertainties and confusion on apportionment. Okay, so our overall question again is how much of the P of the non-point source sector is from ag versus not from contemporary agricultural fertilizer applications? One extra layer before I get into this is that unlike the legacy P built up in soils from past application, the legacy P of sediments presents an extra challenge, which is soil, be it from a stream bank, from a field, as it gets into the stream, it has different flavors or forms of phosphorus that give off phosphorus at different rates. So over some time since the sediment enters the waterway, there's going to be this chronic releasing of dissolved reactive P. We might get a big flush of what might be a soil test P pool, but then there's other forms that will give off DRP over the course of, some studies suggest, decades to even centuries. So this is where the chronic giving off of P that is then that might then be measured downstream is coming from. So just a small percent of the P loaded by sediments will dissolve and thus be measured as export from the state. The majority will probably stay in circulation or stored in these channels. And this gets at then the bigger challenge of how do you quantify the net export? We know how much is entering by bank erosion, but actually knowing how much is redeposited and thus the net, that's a different question. So to put it differently, a big challenge is not just that there's different release rates of different forms of P. We on top of that have to deal with the gross loading of sediments and phosphorus versus the net loading. And that difference is really critical, as you'll see in just a few slides. Some policy background. So that's a lot of the basic stuff. This is where it's applied. Not a single state in the basin, 31 states, account for stream bank erosion as a non-point source. One state, Iowa, now has a working estimate, but that's not in the official state plan. This is changing, but 4 consequences that I really want to highlight. One is that if we're not accounting for streambank erosion within the non-point sector, by definition, we're mathematically overestimating agricultural contributions of phosphorus. Second, we're missing a chance to manage this through things like streambank stabilization programs, which the state has. Third is that we're missing a chance then to use our resource, our conservation dollars, more effectively. And finally, and this is, I think, the most critical one, is that our expectations may not be realistic. It might take us quite a long time to hit our P reduction goals if there's a lag of the legacy sediments giving off P for 50 years. And so, frankly, the deadline to hit our 35% P loss reductions may need to be moved back by quite some time. And if this seems a bit bold to say it should be 100 years back, well, let's talk to the Baltic Sea Basin states that found it might take them a century to hit their goals while they've decreased ag and point sources profoundly. They've had 80% reductions in ag and not in the point sources, but they have the legacy effects still giving off P. Now, this is not without precedent. I am serious about moving back the deadline because the Gulf Hypoxia Task Force has already done this for nitrate. They pushed it back 20 years. From 2015 to 2035, when new evidence arose that you can't just turn off the nitrate tap right away. It takes some time. So there's a need for basic science like this to advance this hypothesis, if it is in fact true that we have these 50-year lag times of legacy sediments, then the plan has to account for that. And by plan, I mean state to federal plan. How does one fill this gap? Not exactly easy. The way to do it is, we think, by combining field approaches with remote sensing, where we can upscale. We can't measure every stream. There's 81,000 miles of streams within our state's borders, from ephemeral creeks to large rivers. You can't do it all. And so you can do a lot of very good work in the field on a few sentinel sites, a couple thousand, as you'll see, and then you can upscale to the other 82,000 miles of streams. Okay, so here's an example. Now, streambank erosion, I'll say, you have to keep in mind that it occurs at very slow time scales. So if you were to speed up the lens of time, looking down from the sky, you would see these streams meander back and forth. And so as the posters describe in more detail, this is a process that is really visualized at decadal time scales, just like the sediments then giving off the phosphorus. So remote sensing lets us go back in time at time scales that then let us understand the potential contributions of these past sediments to modern P losses. This is the lag effect that we can capture. Now, as part of this, we have a new project that is looking at how streambank stabilization measures that were funded by the Department of Ag of Illinois, how effective were they? We've got a great database, and IDA has been fantastic to work with on this, where we can, through remote sensing, understand after something like a streambank armoring was installed, how much did it change the channel migration as a proxy for streambank recession and thus erosion? And the goal here is to inform the NLRS with a cost effectiveness of a in-channel practice. We have in-field, edge of field, there's a third one. It's in-channel conservation practices. More on the contemporary sources, so we can get at historical streambank erosions to phosphorus loading by this way. What about right now and in the future? Future, because we might want to maintain this erosion pin network like Iowa's done for 18 years. They have a lot of potential insights. Well, what you do is you slam rebar pins into the side of streambanks, and we've established now this network of almost 2,400 pins across 475 stream sections across the state. Here's what the recession rates look like. This is the inches per year that the banks are eroding back by. And then as a result of that, the amount of sediment, the pounds per foot of stream length being sloughed off with that recession. A lot of big numbers here. So I've been asked, speaking of numbers, about what's the number? Can you tell us, as a crude estimate, just how much P ballpark might be loaded by bank erosion? And so here's an exercise in uncertainty that we'll walk through together. So we have been measuring a total P content of these eroding stream banks. Most folks assume them in what's been published. We're measuring every single sample of 373 ppm. That's total P, it's not a test value. And we also know that we've got 86,000 miles of streams, and we are losing an average of 229 pounds of sediment per foot of eroding stream. Two assumptions: that we're capturing all the streams in an unbiased way. We're not. We are looking at the ones that tend to erode more. We are making efforts to monitor streams that we know are not visibly eroding, because we want to make this as unbiased as possible. And second, we're going to assume for this calculation that only half of the 86,000 miles of streams in the state are eroding like the ones that we are monitoring. That's the big assumption, and that can change the number by a lot. But again, the idea is to give you a flavor for the magnitude. How much could this be? So if we do all this math, and I'm a soil scientist and not a mathematician for a good reason, so if my math is wrong, please let me know. We get this number: 20 million pounds of P entering streams. Entering, not that it's being exported from the state, but it's entering the waterways as sediment form. And so that's a lot if we think about the baseline we have of 34 million pounds of P. That's half of our baseline losses. I'm not saying half of our losses are coming from streambank erosion, but rather that the magnitude of gross loading, not the net loading, but the gross loading, is magnitude-wise the same order of magnitude as what we're losing as a state. If you assume that all the state streams are eroding as we're measuring them, then that number goes from 19.6 to 39 million pounds of P. However, this is gross load. This is what's entering the stream. Streams will redeposit the sediment back on the floodplain, on a bank, even downstream. So there's this hopscotch or leapfrogging of sediment down the channel pathway. So what's really important here is to understand, when we have this initial loading of sediment by the bank eroding, how much of the P is actually dissolving and floating off, because that's now net export as DRP. How much of the sediment P is going to leapfrog its way down the channel for the next 50 years to hit the Mississippi? So this is part of the answer, but it can't give us the answer of exactly what % of our state export is from bank erosion. But we are getting there. Okay, this then is the tricky part, is those lag times of the sediment. So quantifying how long it takes, and also how much P is stored in our stream channels, we have to answer these questions, I think, to get a better handle on this non-point, non-ag source of phosphorus losses. Okay, so with that, I'm going to transition here and talk a bit about impact. I've mentioned there's basic science that we're doing with NREC support, and then we meld that with the applied sciences. And I think you've seen a mix of both. Here's a distillation of, I think, some of our impact with NREC dollars. We've put out 31 peer-reviewed publications in the last 7 years, excuse me, just on the theme of phosphorus. There's more stuff here not shown on cover crops. And publications are fine. Academics, I think, obsess too much about this. Publications are important because it's the gold standard for policy. It's how we approve practices for the state NLRS. They have a role, but they don't, I don't think impact ends there. There's real world impact, like updating the handbook value. So NREC dollars that you've heard about today are actively being used to update, expand, and to reimagine how we manage a nutrient like phosphorus. We're going to have an MRTP in the coming years to begin to try to offer producers another unbiased resource to consult with. On the other end of policy, we're chewing the food and giving it to the policymakers to pre-digest these findings. This is really important because science does not inform policy. It's the perception of the science that informs the policy. So as examples of this, our lab has gone to DC back in October, and I gave 2 talks on this exact topic. And so NREC funded Illinois data on streambank erosion and legacy P in soils was heard by a consortium of policymakers, including the US EPA, and we think now it's at least on their radar. And it explains some of their own data, where their balances of P for the basin states don't explain what they're seeing hitting the Gulf. So again, if the legacy P hypothesis is correct, it should actually help the USGS and Gulf Hypoxia Task Force get a better handle on the problem. And then more locally, not DC or not federal policy at least, is we're using these results to convene several efforts from SARA 17, sort of the governing authority of scientists who work on all things phosphorus, and with SPA, which is a group of phosphorus-minded folks, to work on how do we define and get a hand on and manage legacy phosphorus in soils with infill practices and in streams with in-channel conservation practices. So leveraging NREC dollars, these are valuable monies that are being paid by the fertilizer sales, and we're well aware of that. I see this as a chance to leverage state dollars to bring in out-of-state dollars. And so to give you a feel for this, we've been trying to, and a lot of the work you've seen is leverage-based from outside groups. And to date, our estimate is $3.2 million that we've been able to bring in from our group by showing a funder, hey, we have an on-farm network for pea trials. You want to pay an extra 50% of that cost invested by NREC for us to add another layer. So dollars beget dollars, and if those are out-of-state dollars, I think that's a win for Illinois. Important because we amplify the impact, not just more mileage on the investment, but also there's more visibility of the efforts and nutrient loss work in the state. And we get more and higher quality answers because we can more comprehensively round out the unknowns. I'll end on this. This is official as of about a month and a half ago, and not yet announced. So STEPS is a NSF-funded center that works on phosphorus. It's a little bit on the engineering side, but it looks at phosphorus from crops all the way to consumption to sewage. And so after some conversations, and because of the infrastructure we have, thanks to NREC, we have established sites, we have established program, we were able to have the U of I join and Illinois be selected as the Corn Belt site. I think that's great news because, again, this will bring in more federal dollars into the state. It'll leverage NREC investments, and it gives us more visibility. And specifically, where we're sitting right now at the headwaters of the Embera, this will be the sentinel watershed for this US-wide effort that involves, I think, 12 states for the Corn Belt site. So the Embera, important, it is a priority P loss watershed for Illinois in the NLRS. So this is an example of what NREC funding can do, I think. So with that, I want to thank NREC for the support and for all the collaborators you saw in that opening slide. And if there's time for questions, happy to take any. Thanks.
Thank you, Dr. Margenot. Are there any questions for Dr. Margenot?
Thank you, Dr. Margenot. The Ambra and the Kaskaskia both have large lakes where they drain into and the water settles and then goes on out. Carlisle Reservoir, Lake Shelbyville, Lake Charleston. Is part of these studies sampling the sediment in the bottom of those lakes? I mean, it would seem to me we would have massive P deposits there, but I wonder how that fits in and if that tells us anything.
Thank you, Don. We're not sampling sediments in lakes or in reservoirs as part of this project. That gets at the storage question of the legacy sediment phosphorus. I think that is the next step in this whole process for all the states in the basin, but in our state is how much P is sitting in the channel of streams as stream bed sediment, but then as you point out, in more static waters, so in lake bottoms. I don't know. It's probably a big number because as we saw from the dredging of Lake Decatur, there's a lot of sediments that can be held. And phosphorus content of our parent material of loess is roughly 250 to 350 part per million. So you think about how many tons of sediment, and very quickly the 350 ppm blows up to be a lot of pounds of phosphorus. So I don't know. From talking to experts on campus that are hydrologists, card-carrying ones, that is the question that they think needs to be tackled. And they say that it would take a lot of effort to get that. So not trying to be dismissive of it, but I think it is a very important one to get a handle on roughly how much sediment is stored in these water bodies across the state.
Doctor, one of your earlier slides showed relative phosphorus yield in different regions of the state. And it looked like, you know, if I'm interpreting it correctly, like the Shawnee National Forest was right in the middle of a high yield area. Is that a a good observation? And if so, would that be a function of centerline changes over years, or what's your opinion that way?
Sure. Just to clarify, Scott, is it this map of balances? Do you mind clarifying what figure?
Yep, what I'm getting at, I guess, is it looks like possibly the Shawnee is in a high yield, area in terms of loss. Is that a good observation? And if so, what would you maybe attribute that to?
First part, is that a good observation? If it overlaps geographically, as I can see, then it would imply that, yeah, there is less P coming out. I would point out that relative to the western basin states, it's still a hot spot, quote unquote. These are also course level estimates too, is worth noting. If it's true that there's a fair amount coming out and it's largely under forested land use, I think this is a prime example of, well, it was deforested very heavily. We have lots of erosion, or we had lots of erosion, and that sediment that may have been choking up streams and creeks at the bottom of the valleys, that sediment is likely still there. There's some evidence from New England, like in Vermont, that the massive erosion downslope led to a couple feet of new topsoil, but some of that made it into streams. And so in Vermont, for their nutrient loss plan, they apportion the legacy sediments and streambank erosion separately to account for that. So that's a long way of saying that I could see it occurring as a result of these legacies of the transfer of sediments from the past ag history of Shawnee.